Hi everybody, we continue in differential equations, section 1.2, solutions and initial value problems. So earlier we defined what is a differential equations. Now we focus on the solution of those equations. So the solution of differential equation is going to be a function of the dependent variable, and a function can be represented in the explicit form or implicit form. So now we focus on the explicit form, meaning y is equal to something of x, for example. So what we mean explicit form, it is going to be something like y as a function of x. So the solution is going to be a function of the independent variable. Right. Now, so differential equation. Once again, we can write differential equation in an equation like that or like that, meaning that we have everything on one side, the right hand side is equal to 0, or we can have the highest derivative and equal to what's left. Right. We may have one example. For example, I can have a second derivative plus 2x y prime plus e to the x y equal to 0. So that equation is in this form. Now if I keep the second derivative, the highest power by itself, and move everything else to the other side, in that case I have the equation in this form. So it's no big deal. Right. Now solution. A function we write phi of x when substitute for y in the equation, satisfy, when we substitute this into this equation, satisfy the equation for all x in the interval I, is called an explicit solution to the equation in the interval I. So we have explicit solution where the solution is a function of x. Usually we call that phi, or could be anything. Right. So let's look at the first example. Show that phi of x equal to x squared minus x to negative 1 is an explicit solution to this equation. So first we have the function is that this one is given. We spent the whole class, the whole differential equation class, to show some certain type of equation. At the first step here, in this section, we just focus on how to verify if the solution is indeed a solution. So if this is given, is that a solution or not? We're just going to verify. We're not going to find that yet. Right. So we have that. Then we take derivative. Derivative of x squared is 2x. Derivative of negative x to negative 1 is x to negative 2. So that is the derivative. And then we take derivative one more time. We have the second derivative. Because this one we have the second derivative, so we have to take the second derivative of the function phi. And then we just substitute. We have second derivative, so we're going to substitute this into second derivative, and that's the function. We substitute that into the function. So we will have second derivative, which is that, minus 2 over x squared times the function, which is that, and multiply it out, and it cancel. Negative 2 cancel 2, negative positive cancel out, so everything cancel out, so 0 is equal to 0. So because it is true, and true for every values of x not equal to 0, because if x not equal to 0, This one is undefined. We cannot divide by x, divide by 0. Yeah, x to negative 1 is 1 over x, and 1 over 0 is undefined. So this is true for every x not equal to 0. So we say that is an explicit solution of the equation. So simple enough, right? So we will be given a function, and then we just substitute into the equation. If it is true, then it is. If it is true for every independent variable, then it is a solution. Right. Now, so we have this equation, right? And the function is given. We need to verify that it is a solution. So the function is c1 is a constant e to negative x plus c2 e to the 2x. C2 also a constant. Now we will take derivative phi prime of x. Derivative of e to negative x is e to the negative x, and then we have to take derivative of the negative x, which is negative 1. Same thing here, e to the same thing, and then derivative of 2x, which is 2. So we have negative c1 e to negative x, and 2 c2 e to the 2x. Right. Now we'll take the second derivative. So the derivative of this is negative c1 e to negative x. Derivative is e to the negative x, and then derivative of the exponent. So just like derivative e to something is derivative is the same thing times derivative of it. Doesn't matter what inside the box. In this case we have negative x, and derivative of negative x is negative 1. Right, and then 2 c2 e to the 2x, and then derivative of 2x, which is 2. Alright, so that gives us c1 e to negative x, and 4c2 e to the 2x. Right, so we will substitute the function into y, the derivative into y prime, and the second derivative into y double prime. Right, so substitute into the equation. Right, so we will have second derivative. By the way, later on we might have some problem that is extremely tedious. So a little more organized will certainly will help. So this is the second derivative. And then minus the derivative, which is this. And then be minus 2, the function and we will verify. So we're not sure if it is equal or not, so put a question mark there. Right, the rest is simple. Remove the parentheses and simplify. So C1 e to negative x for C2 e to the 2x minus negative, that's a plus, minus 2 C2 e to the 2x minus 2 C1 e to negative x minus 2 C2 e to 2x. Not sure if it is equal to 0 or not. Right, now let's take a look. For the C1 e to negative x, how many of those do we have? We have C1 e to negative x, C1 e to negative x, and C1 e to negative x. 1 plus 1 minus 2, so that is 0. So that's good. Now for C2, for C2 e to the 2x minus 2 C2 e to the 2x and minus 2 C2 e to 2x. So 4 minus 2 also 0. So we have 0. We have 0 equal to 0. So yes, that check. So if it is true, then we say the given function is the solution. Is a solution. Right. So just take derivative, put in the equation and check. So that's simple enough. Right. More example. If this is a function, is that solution to this equation or not? So we have the function I'll just take derivative. Derivative of sine x is cosine x. Derivative of cosine is negative sine. And then derivative of the 2x, which is 2. So we have cosine of x minus 2 sine of 2x. So that is the derivative. And then we take the second derivative. So derivative cosine x is negative sine x. And the derivative of this is cosine of 2x, and then it will be another 2. I will just write everything. So cosine of 2x, and then derivative of 2x. So I have negative sine x, negative 4 cosine of 2x. Right, substitute into the equation. So second derivative, that I don't need derivative here, so I can use this color. And then the function, substitute into the function into the second derivative. Sine x plus cosine 2 sine cosine 2x. Now is that equal to 0? Right. Remove the parentheses and simplify negative sine x, negative 4 cosine 2x, plus sine x. Of course, there's a 4, right? And make sure you substitute in the equation correctly. There's a 4. So 4 times sine x and 4 times cosine 2x. Is that equal to 0? 4 cosine 2x minus cosine 4 cosine 2x, so those cancel out. 4 sine minus a sine, so we have 3 sine x equal to 0. And of course that is not true for every x. So because of that, it is not a solution. So it's very simple enough. Very simple. Just take the derivative, put in the equation, and just check. Now, this is a foreshadowing of what we have in the next part. Show that the relation in implicit form define the solution of a differential equation. Here. Right. The reason this is nonlinear, because even if you multiply now, you have 2y, y prime equal to 3x squared, and this cannot be linear. Right. Now, we will get that, take the derivative, and then we simplify that equal to this. If it is true, then yes, it is a solution. Right. So this is a foreshadowing of what we do in the next part of the section. Right. So we have y squared minus x cubed plus 8. That's what we have. Now, since we have y prime, we know y is a function of x. Y is the dependent variable, right? So y is a function of x. So this equation we can write as y is a function of x minus x cubed plus 8 equal to 0. Now we differentiate this with respect to x. So y is a function of x, then we can differentiate with respect to x. Derivative of a square is going to be 2 times that, and then the bracket. Doesn't matter what it is inside the bracket, right? Just happen to be y of x. And then derivative of x cubed is 3x squared. Derivative of 8 or derivative of any constant is 0. So that's all we have. Yeah, I just say this plus 0 equal to 0. Yeah. The derivative of a is 0. Right. Now y of x, or just y, derivative of y, which is y prime. So I will write all of this. It's just y prime. minus 3x squared equal to 0. And so for y prime, it is easy. Move the 3x over. So I have 2y, y prime. Add the 3x to the other side, 3x squared to the other side. And then we just solve for y prime. So y prime by itself is equal to 3x squared over 2y. Yeah, of course that is exactly as this equation. Yeah. So of course we have the equation, we can just take the derivative. But if it is not given implicitly, if it's not given explicitly, we can use implicit differential equation, implicit differentiation to differentiate it. Right? Yeah, if we are given the equation, take the derivative implicitly, and it should work. So similar to that, this time we have implicit form. So in the implicit form, the equation is going to be in the equation, something like this. So we're going to have some function of xy equal to 0. Yeah. So implicit form may be just equation equal to 0. Yeah. On this case, we said the solution is a relation. So it may not be a function. So it is a relation in an equation. It's an implicit solution to the equation on the interval I. Right. So pretty much when we have equation, take derivative, and then substitute into the equation. If it works, it works. Right. Now what we have is x plus y plus e to the xy equal to 0. So we start with x plus y plus e to the xy equal to 0. And now that is what's given. Now the equation is given. On this equation we have dy over dx, meaning that we have the equation of y with respect to x, or we say y is a function of x. Now if y is a function of x, we can just take the derivative with respect to x. Yeah, we differentiate particularly implicitly. Yeah. Same thing here, we differentiate with respect to x implicitly. With respect to the independent variable x. Right, now y is a function of x. We can write y is a function of x. It is not y times x, it is y as a function of x. Now when we take derivative, we can consider, let's put that in the box. Yeah. Now take derivative with respect to x. Derivative of x with respect to x is 1. Derivative of y with respect to x, that's easy. I'm going to write y prime of x, or just y prime. Take derivative of everything. Now derivative of exponential function is going to be e to the same thing, and then derivative of that. Just happen that we have x times y into that. Now, so we have 1 plus y prime and this is just e to the x times y. What next is, this is a product rule, right? X times y. So the product rule right? So in this case, essentially u is x and v is y. So u prime times v plus u times v prime. Alright. Just multiply it out and simplify. Right. So 1. Again, now we write the y prime differently, so we'll focus on that later. Right. Multiply this out. We have y e to the xy plus x e to the xy times y prime. And both of them have y prime, so put them together and factor out the y prime. So put them together. Factor out the y prime. So we have 1 plus x e to the xy. So those two terms have y prime, factor them out. And what's left are those, just 1 plus y e to the xy equal to 0. Now, if we compare this equation with this equation, if we see 1 plus x to e to the xy, y prime or dy by the x, so that's good there. Plus 1 plus y e to the xy. So yes, these two equations are the same. I'm sorry, there is a crash in the program, so I have to restart my computer. When we stop, we show that when we are given this equation, when we take derivative, it is exactly identical to the differential equation. So in that case, we say the equation is the solution to the differential equation. So we write that equation is an implicit solution. Right. We continue. Determine if y minus ln of y equal to x squared plus 1 is the solution to this differential equation. Once again, we have dy over dx. So that means y is a function of x. So we can take derivative implicitly with respect to x. So the equation here, we can write that as a function of x. So we differentiate with respect to x. Right. So the derivative of y with respect to x, we have y prime and derivative of this, I put the parentheses around this, derivative of ln is the reciprocal function and then derivative of whatever inside the bracket. On the right hand side, derivative of x squared is 2x. So I have y sub x, y sub x. Right. So we have y prime minus 1 over y, and derivative of y equal to 2x. Right, I continue over here. I'll factor out the y prime. We have 1 minus 1 over y prime equal to 2x. So for y prime, we have 2x over 1 minus 1 over y. Right, this is not quite the differential equation yet, but on the top we need one more y, so we just need to multiply y top and bottom. So that gives us 2xy, y times y cancel out, so y minus 1. So that's what we have. Once again, this is exactly the same as the differential equation. So the given equation is an implicit solution. Right, so next we have initial value problem, abbreviated by IVP. Initial value problem is a set of differential equations. So we're going to have a differential equation, let's say given in this form. And then we will have the initial conditions. The initial condition is the condition of the function or the derivative at an initial values x0. So x0 is a constant. So we will be given the values of the function at x0 is a constant. Values of derivative at x0 as well. So all of the function and derivative are given. So initial value problem will have the differential equation, one differential equation, and maybe more than one initial condition. So differential equation and initial condition, there may be more than one. Right, so how do we determine that? Here's a little note. If we have the n order differential equation, then we're going to need n initial condition. So keep that in mind. We will check that when we do the example. Right, the example. There's some typo in this one, but don't worry, I will change the one that I post later. So if you bring it out, there should be no typo. So the typo is here. First, it is equal sign here, and there's a subtract here. There's a minus here, and a minus here. Like I said, don't worry about that. On the note I post online, I already fixed this typos. Right, so what we need to check for the initial value problem is we're going to check for the differential equation, and we're going to check for the initial condition or initial conditions, maybe more than one. But on this one, first order equation, so this is order 1, we only need one initial condition. Alright, let's check. The function is x squared minus 5. When we take derivative, y prime is 2x, and that's exactly the differential equation, so that check. Next, the initial condition, when x equal to 1 is y equal to -4. So we say at x equal to 1, y of 1 put 1 in for x. 1 square is 1 minus 5 is minus 4. So yes, it is negative 4. So we say y equal to x squared minus 5 is the solution to the initial value problem. So that's one check. So just like that. So to check for the differential equation and check for the differential equation. Right, one more example. On this one we have a second order differential equation. So since this is order 2, we need 2 initial conditions. And this is the differential equation. Right, the solution is sin x minus cosine x. Right. So 5x equal to sin x minus cosine x. And let's take derivative. Derivative will be equal to cosine x. Derivative of cosine is negative sine. Negative sine is a plus. And then second derivative of cosine x is negative sine x. Sine x is cosine x. Right. Now first we check for the differential equation. Right. Second derivative is this one. Put in second derivative. Negative sine x plus cosine x plus the function is that equal to 0. Right, so we have negative sine x plus cosine x plus sine x minus cosine x. So it's sine cancel out, cosine and cosine cancel out. Yeah, so yes, that check. Now check the initial condition. Y0 equal to negative 1. Right. So at when x equal to 0, y of 0 is the same as phi of 0. Put 0 in for x in this function. Sine of 0 is 0, cosine of 0 is 1, so we have negative 1. So yes, that equal to negative 1. And then we check for the derivative. S0 equal to 1. The derivative, so when x equal to 0, derivative at 0 is the same as derivative phi prime at 0. So we have cosine of 0 plus sine of 0. Once again, sine of 0 is 0, cosine of 0 is 1. So this is equal to 1. Yes, so that check. So yes, so this is a solution to the initial value problem. Yes, so that check. Yeah. So we just check the differential equation and all the initial conditions. Right. Next we have this little theorem. Existence and uniqueness of the solution. So consider the initial variable problem, we have derivative equal to a function of x and y and initial condition. First order equation only need one initial condition. So the criteria is this: if the function and the partial derivative of that function with respect to y are continuous in some rectangle around the point that containing the point, so that there's a rectangle containing the point, then the initial values has a unique solution in some interval where delta is a positive number. Let's see how it works. So the condition is the function and the partial derivative with respect to y continuous. Those are continuous functions on an interval containing the point. Alright, so we have this is an initial variable problem. So more often than not in differential equation, when we have the equation, make sure it is in the right form. So this is not quite the same. So divide by 3 on both sides. Yeah. So make sure it is in the right form before we continue. Right. Or we can write 1/3 x squared minus 1/3 xy cubed. Right. And so where it is, the left hand side is equal to y prime, the right hand side equal to f of xy. So f of xy is equal to this function. Right, and then we will take the partial derivative with respect to y. So the partial derivative of the function with respect to y. Now with respect to y, we can treat x as a constant, and derivative of constant is equal to 0. So with respect to y, this is a constant, derivative of constant is 0. Now with respect to y, negative 1/3, x is a constant. And then derivative of y cubed with respect to y. Oh, sorry, I forgot an x. It's negative 1/3, x is a constant. And then derivative of y cubed is 3y squared. So cancel 3 and 3, we have negative xy squared. So we have two things, negative xy squared and the function. Now, of course, we just need to show that it is continuous on an interval that containing the point. So, what point? The initial condition is 1 and 6. So, around, there is a rectangle around x equal to 1 and y equal to 6. Around that point, the function here is suddenly defined and continuous. This function is defined and continuous. Or I should say there is an interval that containing the point. But I just, instead of write off that, I say around that point, this function and the partial derivative with respect to y those two functions are continuous. In fact, it is continuous everywhere because x and y can be any values. The function is still defined and continuous. So in this case, we say it continuous. If you want to be more precise, are continuous on an interval on a rectangle containing the point 1 and 6. So there is a unique solution. To the IVP. So what we did was we just checked, put in the right form the derivative y prime equal to something, and that function and derivative of that function with respect to y, partial derivative with respect to y, those two functions have to be continuous on the rectangle containing the point of the initial condition. If it is the case, then the initial value problem has a unique solution. Right. So that is section 1.2. See you in another video in differential equations. Thank you for watching.